Excellent. Well, welcome everyone. This presentation will certainly not live up to your expectations, but I'm delighted that I'm surrounded by such amazing people. So the person you see on the screen is David Hilbert, one of the most notable mathematicians we have known. And David Hilbert, when he was 38 years old, so in the year 1900, he decided that the field of mathematics is growing a little too haphazardly, and there needs to be some structure, some definition uh, placed on the efforts of so many talented mathematicians who were active at that time. So he decided to propose a set of problems that have, from that point on, come to be known as the Hilbert problems of mathematics. There were 24 problems, 10 of which he presented in a lecture that he delivered to the World Congress of Mathematicians in Paris. So here's a quote from his paper, and in the interest of time, I'm going to be fairly quick in introducing the Hilbert program. But the general idea is, let's broaden our perspective by looking at these big problems, or what I think are big problems. And in solving these big problems, hopefully we as a field are going to make progress on not just these questions, but big issues, other big issues that we can't even anticipate. This is a nice quote. Sometimes it happens that a man's circle of horizon becomes smaller and smaller, and as the radius approaches zero, it concentrates on one point, and then that becomes his point of view. This has certainly happened to me. In fact, even in my initial academic career, when one is on the tenure track, the whole field is telling you, focus, 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 zero in on a very specific subproblem, so that when the time comes for you to be evaluated for tenure, nobody has any doubt about what specific question and what specific subfield you're a member of, so that the invitations to letter writers can go to just the people working in that subfield, rather than to scientists more broadly who might not even know your contributions. So there are implicit pressures that force us to specialize too quickly, leaving us with insufficient opportunity to take the big picture. And that's what Hilbert was trying to goad mathematicians into doing. Look at big problems beyond just what you have been focusing on. This is a paper that emerged from his lecture at the Paris proceedings. And just to give you a flavor of a couple of the problems that he included. Some of them are beyond my comprehension, but some are so elegantly simple that it's worth looking at. So here is a theorem that was already proven at the time Hilbert was presenting his problems. So any two polygons, it's an amazing result. Any two polygons of equal area can be formed from each other by cutting into a finite number of pieces and recomposing these by translations and rotations. I would not have thought that is the case, but it happens to be the case. You take any two polygons equal area, cut up one, and reconfigure it to be the other. The Hilbert problem that emerges from this is going from 2 dimensions to 3 dimensions. So given any two polyhedra, not polygons, any two polyhedra of equal volume, is it always possible to cut the first into finitely many polyhedral pieces, which can then be reassembled to yield the second? It seems like the theorem that applies in the case of 2D should directly apply in 3D also. But that the answer turns out to be no. It's not possible to do this in the general case. And this was resolved very quickly after Hilbert proposed his problems. I think it was the very first problem to be resolved. So that's one. Here is another one. What is the densest packing of spheres? And as this picture shows, it's the hexagonal close packing that turns out to be the answer. But proving that required quite a bit of work. So this was fairly late in the game to be resolved in 2014. And that's the amount of volume that you can fill in with with hexagonal close packing of the spheres. Okay, here's another one, Goldbach's conjecture. Really simple, something even a grade school student can understand. This is the conjecture. Every even natural number greater than 2 is the sum of 2 prime numbers. Take 8, 3 plus 5, 16, 11 plus 5, and so on. Is this conjecture generally true? Can you prove that this is true? And that has turned out to be, so this is still not proven.
Oh my gosh.
So all that you can do is just take a number and see whether there are 2 prime numbers that you can sum to get it. And that has been done to that number, 4 into 10 to the 18, but no general proof has emerged. So it remains open. So Hilbert's problems were designed to serve as examples for the kinds of problems whose solutions would lead to broad progress in mathematics. We've seen this quote. What was true of math appears to be true of neuroscience now. That is, a lot of activity, a lot of research projects underway, but sometimes it seems unclear whether we are all building towards some grand understanding of the brain. So this is a scene that Jitendra has seen numerous times. Every time we go to the Society for Neuroscience meeting, which is the world's biggest meeting of neuroscientists, this is just a fraction of all of the posters that are presented at that meeting. So this conference has upwards of 35,000 neuroscientists. So every year you get this sense, so much brain power being devoted to understanding the brain, but it's unclear whether we are tackling some big themes or what are the commonalities across the questions being considered. So I felt after one of these visits to SFN, I felt that maybe it's worth undertaking this kind of exercise that Hilbert had undertaken of proposing a set of important questions. But of course, none of us, I mean, least of all me, would have the stature to unilaterally say, here are 24 problems that all of you neuroscientists ought to be working on. So the best that we could hope for is some kind of a consensus view that here are a few problems that several neuroscientists believe are important ones. So in order to get to a stage where one could look for consensus problems, I wrote to the 60 people working in brain science broadly, and specifically visual neuroscience, to ask them to send me lists of what they thought were the top, the most important problems in visual neuroscience. Amazingly, all of them complied. All of them thought this was a good thing to do. And then armed with their suggestions, with their 60 lists, I went off and tried to determine, are there repeated motifs occurring across the lists, or are these completely idiosyncratic suggestions? And so repetitions did arise. There were a few themes that were repeated across multiple lists, and those are what we refer to as the Hilbert problems in vision. Okay, so this was the challenge I posed to them. I'm going to skip through why we focused on vision. This is the place where I took all the 60 lists to. This is in the foothills of the Himalayas. So I sequestered myself for a week in my hotel room, just poring over these lists. It was a really beautiful period. No email, nothing, just lists of paper. So these problems, these 17 repeated themes, roughly fall under these 4 categories: visual information representation, perceptual algorithms, visual development, and cortical function. So we are not going to go through all of the problems that we have gone through in the past. Rather, I'm going to skip to the 4 that I'm told we have not covered. I've talked about these enough times that my memory does not serve me well. So it's possible that we have actually covered all 17 problems in this forum. So forgive me if I'm repeating myself, but
and just to interject,
You can go to the last one and then maybe pick
go backwards.
a couple of the
Sure.
ones that you
Previous,
think
yeah.
are major.
absolutely.
Because we got new participants.
Yeah.
Yeah.
I'm at your disposal. Yeah.
And we were also, we were thinking maybe to share a list of them later and see which ones people are interested in, and then maybe focus this
Yeah.
semester
Yeah.
on 1 or 2
Oh,
and
yeah,
have
that
speakers,
is great.
and we can become more narrowed into 1 or 2.
Yeah.
Or
That'd be
Trying to produce, concrete answers to these questions. Within this forum, so I hope we can get
That would be really remarkable if we as a group answered several of the Hilbert problems. Yeah.
Yeah.
Okay, Amir. So are we?
we see you tomorrow.
Oh, we'll see you tomorrow.
In the
Okay,
cruise.
cool. See you, Amir.
Okay.
Yep. Okay.
Mhm.
So here are what?
Yes.
All good. Okay. So here possibly are the questions that we have not looked at before, but maybe we have. I can't tell. Have we looked at this one?
I think we did it last time.
Yeah, I would remember. We trust
But
you,
we
yeah.
can, I'm happy to go over again.
Yeah.
Well, we have
Very
color
interesting.
scientists here. So.
All right.
Mhm.
So let's then go over this. So this problem concerns the sense that we have that across the entire visual field, the 170 by about 160 degrees of visual field that we have the sense that we have sharp focus and rich color all across the visual field. And this, by and large, is a construction because we know that our acuity in the periphery is nowhere close to the acuity in the fovea. And yet we are deluding ourselves into believing that we are seeing the world as sharply everywhere as we are seeing in the central visual field. Similarly, in terms of our color sensitivity, there is a significant decrease in color sensitivity in the periphery relative to the fovea, and that's a consequence of the really cortotic, the really peaky distribution of cones across the retina. So at 0, this is the fovea, and you notice in the maroon curve, this is the density of cone receptors. So the central 2 degrees of our retina are exclusively cone-based. There are no rods. So rods are these cyan curves. So only cones in the middle. And then as you move away from the fovea, very rapidly, you have this fall off in cone density, and it's mostly a rod-based system outside of the fovea. Despite having this great disparity in terms of color sensitivity in the fovea versus in the periphery, we have this impression that our color saturation across the entire field is about the same. So the Hilbert problem is asking, what is the basis of this pan-field color and pan-field focus? How do we achieve these percepts? Is it a kind of a filling in process? Is the brain actively filling in the high spatial frequency details and the color information? Or is there something else? We simply don't have the answer to this yet. Yes.
Question.
Yes.
Sorry.
Mhm.
But have you verified? It's proven? Sorry, I don't come from visual
Yeah.
neuroscience. So is it proven that if I look at an object from this angle versus that angle, my color acuity is okay?
Yes.
Sorry,
Yeah.
there are color sort
Yeah.
of scientists tell me.
So it's not the case that we have no color sensitivity in the periphery, but you need to increase the size of your color patch in order to be able to detect color in the periphery.
So, but then you're saying that the perception is that it's uniform, even if it's
Right.
Okay.
Yeah, so let's set aside color. It's a little more tricky, but focus, the sense that I'm seeing you in sharp focus, and that's not mysterious because your image is falling on my fovea. But then why do I feel that I'm also seeing Myung in sharp focus? Clearly, Myung is falling in my peripheral retina, where my acuity is poor. Yeah. So this whole field of filling in processes, it's a fascinating but largely mysterious area. Charles?
It's a very interesting filling in result. I think I showed with Sid a few days ago that if you were to take a heterochromatic, so there's two colors, it's essentially a disc, or like, let's say a full disc with an annulus around it of a different color. And if you were to, essentially what they do is so there's a phenomenon of like fading of stabilized images. So if you stabilize the image on the retina, then the image fades. So if you were to not stabilize the outside edge, but only stabilize the inside edge of the image, so there's a border between the disc and the annulus. If you stabilize that on the retina, but keep the other one sort of moving with your small eye movements, and what you find is the inside disc sort of gets filled in by the color of the annulus, which is very interesting. And you experience that inner disc is the same color as the
I think
annulus.
this is one of the first experiments tested for filling in I think 1960 or something.
Maybe 60s,
using this like the particular like contact lens kind of projecting like
it might have been that preparation.
Particular contact lens that has a projector
Mhm.
attached to it,
Yeah.
and that's how they do like how
The
the
stabilized
image retina stabilization can actually induce the filling phenomenon
Yeah.
with the red and
Mm.
green. It's very like strong.
It's very interesting that the edge disappears and then the color sort of in your perception fills in.
How long does it stay there, or is it? I mean, like that perception of it filling in, does it change then?
As long as your eye retina is stabilized, you always have filling in. So,
You always get the sense that the outside color fades in.
So I'm not sure exactly, like maybe it's a little bit intermittent because stabilization is
It's hard.
imperfect.
but if you make a very strong, like perfect stabilization, theoretically, you will have the filling in all the time.
Yeah,
So of course, like in real life, like if you blink or anything, that's stable. So that's why you like those filling is breaking. But
So this also relates to the question of why do people with severe visual impairment develop large movements of the eyes. So if you have a really degraded visual input, then as Charlie is pointing out, it's essentially approximating a stabilized image and the visual input is fading out. So is the brain now trying to make large eye movements to try to get some stimulation to the to the ganglion cells in order to give some input, keep some input going to the brain.
That's very similar to idea about why people has microsaccade enhancing like high special frequency information, like generate like very fine like movement, which is like the size of your chronoceptive.
Yeah.
And so with that idea, why people has more like larger like fixation like on eye movement in periphery. If you fixate with periphery, those the involuntary eye movement is much larger. Some people argue that maybe that's kind of because of the periphery receptive field is much larger than fovea. So that's why you need to move larger to actually have more, input enhancing this like image enhancement. So that's kind of one of the I'd say ideas.
Maybe it's the tremor.
Blur, maybe the same. Tremor. So yes, people using a microhookah, you should replace that with.
Which also related to this, did you really like Marge did some work with visually deprived monkeys, and they developed the nystagmus. Were you aware of?
So I know that she had been working with deprived monkeys. But I didn't know about the nystagmus.
Yeah, she told. Yeah, I was talking to her in a little email chain. A couple of interesting things.
So this is Marge Livingston that Charlie has been in touch with. Marge is a neurophysiologist at Harvard. She was a collaborator of David Hilbert, and David Hilbert and Marge Livingston did a lot of work on the magno and parvo distinction.
Yeah. So she says that binocularly deprived monkeys, I think a year deprived, developed this nystagmus. Also, she was saying something. She has a monkey who like wore vertical goggles for a year. I'm not entirely sure what that means, but she said he might have vertical nystagmus. So maybe it's like going up and down. I need to inquire about this, but it's very related to
that is
repercussions.
Right. We would love to understand what is causing the development of nystagmus in the Prakash children.
The nystagmus in the Prakash kids is just horizontal? Or
we haven't quantified that. That is something we have to do just by eye. Yeah.
So one thing that I can add to is that several years back, Valentin Dragoy and I had done an experiment in monkeys in which we made them to look at natural scenes doing free eye movements. And we were trying to see if where are they making the next saccade and what is at that saccade. So we make like fixation saccade, about 3 to 4 saccades, fixations every second. And in between, we dart the eye to somewhere else that we are looking at. And when we did the analysis of those fixation places, what we found was that there is a greater propensity for making a saccade, next saccade, to an area which is different from where I'm currently fixating. So the sum total of that paper was, it was published in Nature Neuroscience, that our vision tries to enhance differences rather than similarities. And that is like built into that the next saccade will be to a location which will have a totally different feature as compared to what I'm looking right now. And that way we try to integrate as much of information from the scene we are looking at, and make like reduce redundancy.
That's very.
Yeah, not to put you on the spot. What's your question? Lisa's question that you work on in color vision?
My research. What I'm currently doing is try to compare the asymmetry between our perception on the achromatic increment and decrement. So the perceptual scale and pedestal discrimination differ qualitatively for us when we are trying to perceive white squares and black squares.
So is this related to like the simultaneous brightness illusion or simultaneous contrast illusion? You have So a step up and a step down on two sides of an image, and or two identical squares on two sides of an image, and based on the background, one seems like a step up and one seems like a step down.
In the experiments I did the experiment separately. I didn't put the black and white squares together to make the comparison. So I'm not sure about that.
Okay. Thank you. All right. So, Arvind, to your point, so here is a plot of our acuity as a function of retinal eccentricity. So at the fovea, we have 20/20 vision if we have normal refraction. But as you move away from the fovea, you notice that the acuity is falling down. So by the time we get to, say, 50 degrees out, we have worse than 2100 vision, significantly worse.
And that's a very small distance that your acuity drops. Like if you look at the axis on this graph, and then try to read where it says nasal. At least I can't read nasal, which is like just a tiny,
just a tiny little bit away.
A couple degrees or something away.
It's only for form.
For form, yes.
Adjacent motion fields.
Yes, right. Yeah, so motion we are able to do quite well in the periphery. Yeah. I feel hesitant to say any more in Myung's presence. Myung, you have been looking at these kinds of plots for much longer than that.
But I think we should also highlight that these are measured by thresholds, right? Like, like make it using finding out what are the smallest visible the stimulus intensity, either contrast or size, for a person can detect, right? However, in real world, so that's a threshold visual cue size or contrast. And however, in real world, daily life, everything is all high, super contrast, right? So which is way above our threshold.
Right.
When it comes to way above our threshold, our perception is completely looks homogeneous, right? But actually, when we measure in the laboratory, measuring what are the smallest the stimulus intensity people can detect, that is then we get this kind of thing. So there's a discrepancy between threshold level and then and also supra threshold. So I think there's a kind of like we have to make up, recognize the difference, right? So
so if one possibility for explaining this illusion of pan field color and pan field focus were to be an outflow of information or a filling out of information from the fovea to the rest of the visual field, then that would make an interesting prediction. And maybe we chatted about this the last time we went over this. For patients with macular degeneration, is it the case? Is it the case that their sense of pan field color and focus is degraded? So do they no longer see the rest of the visual field as being in sharp focus and color because their macular region has been damaged?
Actually, that's a very good point. And we know that they don't have any very good the color sensitivity. That the color vision is fairly impaired. Even impact periphery, remaining but that's a good point. Whether it is because of the macular damage, actually. Other like in the worsening of their perception on top of their actually low-level sensory deprivation, right? So I think there's a two different mechanisms may work. So that would be a very interesting experiment. We can easily do with simulate scatometry. Oh, okay, one experiment down.
Charlie,
anybody right down. I already forgot about the experiment. We talked about this already before.
Yeah, 80 years from now, when we are both in our hundreds, we would be. We
still. Have you done that? Because we didn't make a note. I'll make a note.
But things in your periphery aren't like contiguous with like the objects that are colored aren't contiguous with the things in your focus. So how would it?
So it would be some kind of a statistical outflow that in the foveal zone, I recognize that this is a forest scene. Hence, I expect this amount of green and this amount of brown out in the periphery. So it's a fairly intelligent kind of out.
But then if you change the color to not match the statistics, then you would expect you'd still see it in green, right?
If you change the color of the periphery.
Yeah.
So we did not quite that, but something similar to that. So Ben Ballas, when he was a PhD student here, he created these color chimeras, chromatic chimeras, we call them, where you had color in the foveal zone, and then it kind of, in a feathered way, desaturated to just gray. So the image was colored in the center and then gray everywhere else. And when flashed up quickly, so that you didn't have a chance to examine the image via eye movements, people were very likely to perceive it as a full color image.
But maybe sort of also building on what Charlie mentioned, right? What if we sort of show them a picture that's your poster, but what's outside is not what they're used to seeing, right? So the center part is forest, but everything else is
Beach, yeah.
something, right? And then do they?
Statistical image.
It's
Right,
statistic,
okay.
non-statistical
Yeah,
images.
yeah. Or like unusual.
Yeah, and then is the accuracy or perception
It's a
similar?
very interesting point.
It is, right.
Yeah.
So if the periphery has enough low frequency information that you can actually recognize that this is a beach scene, the center is a forest scene, what does the brain do? Would it still insist on flowing out the forest-related information to the beach scene, or
Is it green or yellow?
Yeah.
Very interesting. I have no prediction.
Also, instead of flashing it, you can use Neon's gaze contingent.
contingent, yeah.
We can actually present two different, completely like incongruent scene portion parts, right? The central and periphery, and first the comparing the color perception or like those like other like perception congruent between the incongruence. That would be very interesting.
Yeah.
If its periphery is all about summary statistic and we like texture summary statistic, which is like continuation of the phobia, then we would expect the complete like brain would be complete, not have like filling in process as usual, as much as the one who's like continuous statistic.
Right.
And this would be harder, but is it possible to look at other activity? Brain is also not well understood. In the brain that is doing the extrapolation or something like this part of, but that's also not understood, right? The part of it.
So whether you could record from the part of the brain that is actually responding to the peripheral zone and see whether it's being driven by
rather responding to the foveal sort of image and extrapolating. Is there? I don't know. That's a study. That's
no. I think that's a great question. So is this illusory focus and this illusory color, does that actually drive activity in the brain?
Some part of the brain, and you can understood.
So there are traveling waves in visual cortex that spread pretty rapidly. If you just flash like a point of light, then you have over, I don't know, what is it, like 50, 100 milliseconds, it sort of slowly spreads across the cortex, which is super interesting. Maybe related to like filling in or this filling in the periphery or whatever it is.
And you would think that there might be an asymmetry in terms of how information flows from the foveal part of the cortex to
that
that
would be super interesting, actually. I'm not sure. But
cool.
I have a question.
Yes, please.
So the color chimera you just mentioned is chromatic center and achromatic periphery. Sorry if I missed that. Is there any study like do the reverse, like achromatic in the center and chromatic on the
and that leads to false reports of the entire image being gray.
Is that the case when it's like an image of something real that the person could quickly recognize, or is it? Like, does it have to be like a real object, or is it like random blobs and
So I think we did that. and I should remember this, but it's now 16 years ago. But I'm happy to send you a copy of the paper.
There's a paper with colors.
With Ben, yeah.
Red colors.
Yeah.
Oh.
I think it's called Fanfield Color.
Oh, okay.
Sorry.
Mhm.
Oh, this is a crazy idea. I don't know.
Of course. From Charlie.
If filling in actually occurs, will there be a way to like disrupt it by like when you flash the stimulus, maybe over like 50 milliseconds you have some filling in one way or another?
So something like that has been done for regular filling in, like in the blind spot, or some other artificially induced scotoma. People have done MEG studies of stopping filling in. I don't remember the details. But yeah, so if you were to disrupt activity of the wavefront, so there is information that's going to go into the scotoma, and you disrupt activity in the periphery of the scotoma, then you can leave the scotoma unfilled.
Oh wow!
So it's by like long range horizontal connection, then you're actually interrupting the stream.
Right.
That's really interesting.
Yeah, Charlie Gilbert had done this experiment.
Charlie Gilbert.
Yeah,
Oh,
Charlie Gilbert
Oh,
at Rockefeller.
Charlie Gilbert, right. He's at Columbia. Is he still at Columbia, do you think?
He is at Rockefeller, I thought.
Oh, Rockefeller,
He
right.
used to do like I movement stuff, right?
Is he now?
No.
I think he's retired now.
No worries.
It's okay.
I'm okay.
You know, right?
There's a white
Mm.
the white lines.
Yeah, so it's Charlie and Torsten.
Mhm.
Right, you're right, Jitin. Torsten and Charlie worked together at Rockefeller. So they looked at tracing these long-range connections in V1. Yeah. Oh, and we are close to
I might finish the four.
As usual.
these Hilbert problems have been
No problem.
this millstone around our neck. They just never give up.
For the next 100 years.
We're getting
Yeah, we're getting somewhere. These are all very interesting. Did we do this also? We did.
No, what
No?
is that?
No less a person nice.
Great. So, okay, let me first read the main question. What is the longitudinal progression?
Oh, I know, we did that.
We did?
However, I think we should do that again.
What is the longitudinal progression in the list of objects that an infant can recognize in the first few years after birth? And how does this relate to specific object attributes and developmental milestones, such as motor dexterity and language? So if you were to make a tabulation of baby first recognized the feeding bottle, then recognized the pram, and then so on and so forth. So in terms of time at which the baby is first recognizing these things, would there be some kind of a meaningful progression across multiple babies? Or is this just the contingencies?
Idiosyncratic.
Idiosyncratic. So, okay, so that's the question. Any thoughts about whether there would be such a progression? Would some categories of objects be recognized sooner than other categories of objects?
Well, I guess you need to have a control for like interaction, how much environmental like influence, right? Some children, like kids grew up with particular environments, like a particular type of toy or thing. They might have recognize what's better. So you need to, I think, like how to answer this, how can you actually remove those environmental factor, and then actually whether this is intrinsic kind of developmental thing, property. That's the they're basically asking, right? Like once we be able to remove those influences, right?
Possibly like feeding bottles in a different square shape or I don't know, cuboid shape or something, so that does that help them understand cuboids better or earlier maybe or
so baby without any training exposure. It's very difficult to test.
Yeah, so the reason we bring up Einstein in this, so no less a person than Einstein was fascinated by the question of what an object is. And that question might have some relevance to when different categories of objects might be recognized. So, so let's just think about what is the minimal definition of an object. If you divorced it from semantics, that's the glass, those are glasses, etc. How would you define an object? What is an object?
Object is something I can act on.
Okay, so that's
But
one
it's not
definition.
animated. Something I act on, inanimated thing, but how an entity that I can act on.
So why do you draw that distinction between animate and inanimate?
Animated could be humans, right? Like
Yeah, but an
animal,
object, a human is an object, no?
human. Because the object is always has a property have that the static, right? Like it is stationary. Of course, its ball is rolling, but however, animated is involuntary movements which I cannot control over. So
You
that I
also
think that's different.
Think
Right?
because it should have a fixed form, humans can change form. Is that what you're saying? Animated versus
Yeah, human can like motion, biological motion is involved, right?
But I would think that we ought to allow for objects that can change form.
No, yeah. So I think that's kind of I actually distinguish why have to be inanimated. Once it's animated, it's any kind of the biological motion is involved, which is I won't consider that as if anything entity that actually have a biological motion, I won't consider this object. Would you?
Okay, so that's well, it's
But that's my own like.
okay.
Yeah.
Interesting stand. I wouldn't have.
Would
Got
you
that.
consider a cat as an object?
Absolutely.
But maybe for visual computer vision,
Oh,
if from a computer vision you think they're rather than you think they're more
I
like
see.
the natural world.
Oh, okay. The people more general term than object is anything.
Yeah, so object very broadly defined, even if you can't name the object.
I think anything that has mass.
Okay.
Yeah, that's okay.
Yeah.
Then
I mean, even the light bulbs are objects.
Yeah, yeah.
You can't see
Okay,
them. There's
yeah.
no
Yeah.
light. Like,
But how do you like determine like where the boundary of the particular things are, right? Like that's part of the boundary. Like what?
Right.
Like a house. When
house
like the
object.
whole.
Yes, so an object can have internal structure. An object can be made up of other entities. But what would you think about the following definition? I'm trying to go to the simplest possible definition. So an object is a cohesive entity. So any cohesive entity is an object,
Yeah.
whether it's a rock or it's a cat. Everything that's part of that entity sticks together.
what is an example?
So
Of
it's
incohesive?
incohesive gas.
A river.
Gas or
A river?
river, water, water one object. Because
Yeah.
fire is one object because you keep moving.
Yeah, right,
Rain is
yeah,
not.
right. In,
Sorry.
in,
A drop of rain.
in a poem, right.
A cloud being
Cloud.
Yes, so a cloud is an object at the distance we are viewing it from because it's a cohesive entity from that distance. But if you are close to it, then
It's not.
I wouldn't think that it's an
How
object.
about entangled electrons? They're
Entangled.
far away from
How
each other.
How about black matter?
You measure one of them.
Yeah. I don't know.
Consciousness and object.
No, so the reason I
Not your consciousness, not cohesive.
So the reason I'm going with that definition, that an object is a cohesive entity, is that it immediately brings in motion as a litmus test of an object. So what do we mean by cohesion? We mean that these things stay together over time.
Yeah,
Right.
fate, same fate.
Same fate.
Like
Right.
what is a gestalt psychology, right?
Right.
The common fate.
Right, exactly. So if that is our test, that things that we are calling individual objects will move together then motion becomes the primary driver of the definition of objects. That the things that we are seeing as moving cohesively, we are going to label as objects, and that then begins to intersect with the question that's being posed here, which are the things that we would first recognize as objects. We would recognize the things that in our perceptual history have moved together.
And that's different what our perception uses as a criteria and what actually is an object, right? Because if a person is driving a car, they'll be moving together.
Yes.
But if you're looking at it, they're not one object with the
And
person in the car.
And I would say that that actually happens. In fact, there's experimental evidence to that. So some of the work that Phil Kellman and Liz Pelkey did showed that if you have two random objects, one sitting on top of the other, if they move together, the baby tends to see them as one object. And in fact, subsequently, if you move the two independently, the baby is surprised.
That's cool. Excellent.
Baby is surprised. So on that tangent, those of you who like Monty Python should check out the clip of "Surprise Your Cat." So they
Confuse the cat.
confuse the cat, right?
It's a good one.
It's a very good. I mean, these are all perceptual things that a little toy goes in here and then does not emerge, and the camera cuts to a cat who is looking very. So on that line, that motion might be important for defining what objects are. I wanted to tell you about this finding from Prakash. This was one of the early papers from Prakash. So we would show all of the Prakash children this collection of object images, and we would ask them to try to name them. After we had looked at a few of these children, we started noticing something quite interesting. So these are results from 3 of the participants, SK, JA, and PP. So here are the findings. So the dots here correspond to which of these children were recognizing that object. So look at the objects that all 3 children recognized. Those, right? Most of them are the ones that are likely to have moved in the child's experience. So these black bars that you see are ratings of motility that we got from other observers. So how often do these objects move? So
It's a tree, right?
right. So there are a few exceptions. So there is the exception of the tree, and there is the Pepsi bottle.
I think there's familiarity.
Right. Right. Every
Just
child
like cool.
recognizes that.
That's how long after surgery?
This was maybe 2 months after surgery.
2 months?
Yeah.
What do you mean by recognize?
They name it. They named the object.
And they experience all the objects during
In their
life.
Yes. Yes. So we asked them before they were shown any images, do you know of such and such object? And they have in the daily experience. They certainly handle keys, they handle the bulb, and so on.
So they could name all those objects.
They could name all of these objects. Yes.
How old were they? Sorry.
So I think the youngest was 8 and the oldest was 29 years. So 8 years to 29 years. These are the Prakash participants who had been blind for the first several years of life and then gained sight.
Is there a possibility like or some objects they are exposed to more like the flag of India like multiple times?
It's possible. It's certainly possible. Yeah, so this one should just take as an interesting kind of coincidence that the high highly motile objects are also the ones that are more likely to be recognized, but they could be alternative explanations.
For those
Yeah.
shoes and socks, that's something they wouldn't recognize that
Mm.
they probably use every day.
Yeah.
That's
The
really
bird is also.
Well, socks never look like that.
Right, that is-
Elephant, is the elephant?
Yeah.
Elephant?
Yeah, that's an elephant.
Is elephant very common in India? My friend Amy's weddings,
Yeah,
the groom
yeah,
brought
yeah.
the elephants.
Vishu came on an elephant, right?
Yeah.
Yeah, yeah.
Oh,
Mm.
that's like very interesting. I recognize elephant.
Were they asked to describe the order of those things so they're not actually recognized things around that object as also part of that object?
No, we just asked them to name the central object in the image. So you would have wanted them to describe the rest of the scene? Or?
Yeah, for example, the tree.
Mhm.
I wonder if they are recognizing the tree or also the grass around it as part of tree.
Mm.
So if they
Yeah.
can mark the border.
A fair question. We didn't do that.
And how rigid do you expect these objects to be? Like in terms of like in the molecular level,
Yeah.
Their orientation may change as they
Mhm.
go. Like what's your expectation of their, stick orientation?
Mm.
Like a dough, for example, that you throw in
Yeah,
the air
yeah.
can kind of change shape.
Yeah.
And
Yeah.
would that be considered as an object, or like I think there is certain threshold, I guess.
Yeah, that's an interesting question. I don't have a good answer as to how much diversity in the shape can we tolerate and still keep thinking of this entity as an object.
Mm.
Um,
Apparently socks, for example,
mhm,
when you move them, they might change shape.
mhm, mhm.
And that would
Yep.
because they may be correlating the color, texture in
Yep.
different,
Yep.
partitions of the object. And when the orientation change, they
Yeah. Yeah, so some work that Sid and I and Lucas and Marin are doing on looking at how we create object models. Our thinking about the object model is not just as single snapshots, but rather views of the object that are tied together because of temporal contiguity. So to your example of a sock taking on different shapes, so long as those different shapes occur in close temporal proximity, the brain would stitch them together, and that collected set of appearances would be the model of the object rather than any single snapshot. So this to the question of what is the sequence in which the brain comes to recognize objects. This is one possible hypothesis that maybe that sequencing will be based on how motile the objects are. Moving objects come about first and then later the static ones. Okay. So I want to be respectful of people's times. So we're going to look at just two more questions. So here's a simple one. Simple.
I can solve it tonight.
Yeah.
Are there others that we haven't seen before?
I don't think so. I think we are.
Do you want to go through them quickly?
Yeah, what is
I
it?
think there was we still have, we have
So-
I
not,
feel like there
we
was
have not
some.
completely covered.
So-
everything.
Yeah.
The causal dependencies between basic perceptual constancy.
No, this is, we didn't do it.
I
Didn't
don't
do
think we
that?
did this. What about the previous one?
So
Is there any?
yeah, this is
Recording.
interesting one.
Oh, we did this.
We did.
Yeah.
Okay.
Yeah, I think that one.
So
What
this
was
we
the-
didn't.
Was it causal
Go back.
dependence?
Sorry.
Before?
The one just before
One
this,
back.
the short one?
This-
Oh, yeah, these, we haven't seen any of these.
Yeah, we haven't seen this one.
Basic. So we'll have to have another session.
What's that?
Did we pick and choose?
I think you did.
Yeah, I think we
there was
had
one
like a
time we
bunch.
jumped somewhere.
Oh,
Yeah.
we jumped.
I think we
Oh.
did jump once.
So what should we do?
We need another session.
We don't do this?
Terry
Why
has a
do we have to
comment.
cerebral? Sorry, who?
Terry made a comment. so
Yeah,
that-
Jerry?
Sorry, I just was going to mention because I used to study developmental neurobiology of children with autism, and very much of your ability to differentiate and recognize objects has to do with your motivation to learn what they are. I mean, if they all often have problems with only recognizing a part of the gestalt, so not seeing the whole car, but only seeing the tires, or and maybe they're motivated by some of the. In general, humans might be motivated by some of those objects on your list more than others. They could be interested in their hand because it's a part of their own body, or something that moves because they see it as something as a potential threat, or something that's more interesting than something that's stationary. So just to keep in mind that aspect of a lot of your development of what you're going to remember and what's going to have saliency to learn has to do with motivation.
Yeah, I completely agree. And so this story of motion predicting what would be the objects that enter into our object lexicon, that's at best only a part of the answer. I totally agree that the motivation to acquire knowledge about certain objects is a very important driver. Yeah. Okay. Should we?
Since you have shown us.
Yeah, we've done this one.
We should go. Oh, we should go through this. All right. So why do we have two cerebral hemispheres?
Repeat it.
What?
All right, I'm sorry.
Charlie is disappointed that we're taking it.
That's okay, we can. It's
So-
pretty good.
So why do we have two cerebral hemispheres? It's an honest question.
Get 3 dB more sound intensity,
Because we have.
3 dB.
Is that right? We get 3 dB more sound intensity.
Why?
It's double.
What you mean?
Doubling the.
But why does it have to be organized as two halves and not just one block?
Or like,
Is it
or
arithmetic?
octaves?
Yeah.
The distributor, like.
Yeah, peripheral.
Yeah.
So, okay. So one way to approach this question is by considering the consequences of removing one hemisphere. That'll tell us how critical two hemispheres are. So there are these cases that I probably mentioned in the last discussion, cases of hemispherectomies that I'm sure Sid has seen. So children who experience certain kinds of intractable epilepsies, in a small number of those cases, the only life-saving treatment available to the surgeon is to completely resect one half of the brain. So after the surgery, the child is essentially living his or her life with just one hemisphere. And you look at CT or MRI scans of these children, and they are age restricted.
Yeah, I mean, we can't do it after.
Right, exactly. Yeah, so these would be children. I have only seen like 7 or 8-year-olds at the oldest. So their brains are literally half brains. The rest of the cavity is filled with cerebrospinal fluid. The remarkable thing is that these children, other than some motor clumsiness, they are able to do most of the things that they were doing prior to the surgery. Language, recognition of people, even if the right hemisphere is resected, their face recognition skills are still intact. Or if the left hemisphere is resected, they're still able to acquire language. So the question then becomes, why did we have two hemispheres if one is so dispensable? So I think that's why this
And it's
Hilbert
not
problem.
just humans, right? Like, we can see the same two hemisphere anatomy in different animals, so different creation.
So I don't know. That's a great
Yeah, where
question,
in the
Shoaib.
evolutionary
yeah,
tree
where
does
is
it's not, is it no longer?
No
the
longer
case?
necessary. If Jitendra, hey, Anchal, you've joined.
I'm sure.
Oh.
You should be asleep, Anchal. 4:30 in the morning in India.
That's our best hours.
It's early finish.
Jitendra, are you still around? No.
Yes, yeah, I'm here.
You need to go up and down.
Okay. So, Jiten, do you have an answer to the question that Shoaib posed? Is the redundancy of the cerebral hemispheres that humans exhibit, at least in cases of hemispherectomies, that seen in most animals, or are the two hemispheres more necessary in other animals?
Interesting. Like most mammals do have two hemispheres. Probably all mammals have two hemispheres. And so just a tangential note. Yesterday I was in a conference at an NIH conference, and there was somebody who was explaining the usefulness of ECT, so electroconvulsive therapy. And it has been a mainstay of like depression and anxiety sort of alleviation for a long time. And what was interesting, so one of the issues with ECT is that people do have sort of remission from anxiety, but they also are instances of high amnesia, so they lose memory after an ECT. So this person at NIH, what she has done is that they tested whether you can reduce the amnesia by putting the electrodes on the same side of the head. For example, only zapping one half of the brain. And what they found was that these people do not have that profound an amnesia, and they recover most of their memories pretty soon. And the reason is that the other half of the brain, which was not zapped, the memories from there they start to get transferred to the other side. So that is like one way that you can explain that the redundancy improves the survivability of the brain function, even if one side is partially sort of made sort of dysfunctional.
This question that why do we need the large brain when half size would suffice, as opposed to why it's organized into cerebral, right? So it could be organized into one large semi-cerebral sphere, I guess, then in that case. But the point that I think Jiten seems to be that the other paper is half of it is mostly good enough. Half size would have been good enough mostly. But
would have been right. And Jiten is pointing out a really profound kind of redundancy, that even the memories, it's like a second copy is available in the hemisphere.
Yeah, and it gets transferred to the other side. So the amnesia issues are much less in these people who are zapped on one side.
I mean, so much as I would like to believe in the redundancy story, neural tissue is just so metabolically expensive. It's hard for me to believe that we would, or nature would, invest so much
Even the one hemisphere has enough redundancy to dispense all these functionalities and create support. I think so, because I believe that there are so many parts of the brain that we can't even figure out how they are going to serve specific purposes.
So in cases of stroke, Jiten, is it the case that if you have a stroke on one side of the brain, is there any indication that the homologous other side begins to be more involved in that function?
I don't think so.
I don't think there's a hard evidence for that. So in the sense that like new connections get made, which will sort of compensate for the the area that is now dysfunctional. And there's a rudimentary sort of recovery of, say, motor activity or some of the functions that have been lost with this thing. But whether the other side of the brain compensates fully and takes over some of those functions is there's no hard evidence for that.
Arvind, I'll make just a quick point. So do you think there's any similarity to this question about why we have two cerebral hemispheres to the question of why women have two X chromosomes? So is the presence of the second X chromosome protective, and is that a deliberate attempt on the part of nature to have that redundancy built in?
That's a great. Great, something that has been sort of preserved by the nature. That's an interesting question.
Yeah, it says the early vertebrates already had it, so.
The early vertebrates had two hemispheres.
Yeah. It's
Flies have
very
two
early,
hemispheres.
yeah.
It's extremely.
But only vertebrates? Non-invertebrates do not have two flies?
Flies have two hemispheres. Yeah. Or I guess it's not like the same. It's not really like cerebral hemispheres. It's still like bilateral symmetry. Feel like on globes or whatever.
Could it be that this is just nature's way of efficiently organizing the brain tissue to split it into two?
Yeah.
It could have been smaller or larger is probably, but maybe this asymmetric distribution of, I don't know, makes a little more sense from a blood circulation or some that perspective to have it as opposed to a
right. Yes. Yeah, so it's more the low-level plumbing kinds of efficiencies.
Possibly. And then whether half of it, even if it was half the size, would it still be in two sort of hemispheres as opposed to single one?
What are the exceptions, or I mean, like, is it because, and also our bodies are symmetric? Is that also consistent, or I mean, other creatures who are asymmetric, they also have that. Like, is it something based more on body that sort of built on top of that architecture?
That this is just a common plan for constructing organs that we are following.
Yeah.
So again, very naive answer. So the fact that we can modify our genetic structure to make just one heart rather than two. Yeah. So potentially, nature could have come up with a design that only had one hemisphere, right? And yet, for some reason, it seems to have been adapted to have two.
But the same question can be asked, like, why do we have two hands? For the most part, we could, if there was only one hand, we would have survived, like, or like we have multiple, like two eyes, everything is double. Is that a redundancy which was by design, or it is something that made us more
physical
survive?
Component coming in, right?
Yeah. So with limbs, I can see a story of like locomotion and the fact we emerged from quadrupeds who need four limbs, and then we just started using our front paws.
You have two eyes. You can have one eye.
No, the question, why do you have two nostrils? Hearing me in the two eyes.
That's perception.
Yeah, that's
People like a two eyes.
Two eyebrows?
Yeah.
Well, one
I
pretty
know
nice.
that. I know this.
All right.
This is kind of
I think this is.
design of our body.
So when people begin talking about why we have two eyebrows, I think the evening is done.
That's more intellectual conversation.
Time for Chinese with Korean whiskey.
Oh, wow. Okay, yeah. So after we conclude, we'll have Korean whiskey.
Yeah.
I'll bring up, I guess one point that I brought up before is that your visual field is seamless in the middle, and yet we have two different. I mean, each one of our V1, V2, whatever corresponds to whatever one hemifield. So how do you accomplish that?
And there's no overlap at the level of V1. Absolutely no overlap between the two hemifields. There isn't a cell in the right hemisphere that's looking at any information in the right visual field. Yeah.
How you need like the same integration across sort of that central seam as you have integration like, within each hemifield neighboring spots.
It's the seamless stitching together of information from the two sides.
Yeah, that's.
All right. We
more?
Really? 7:15.
Why is unjust brain like connected as a blind if it still has two separated as two hemispheres? Because either you have two hemispheres, I mean it's still like left and right, but why not its entire ball?
Why does like this?
Yeah, why is there a gap?
Yeah.
I would say aesthetics. I know it's not
Aesthetic, right?
Symmetry studies.
Yeah. So when we arrange marriages, we also present MRI of the other person's brain. That's how beautiful, right?
Okay, that's a
Yes, indeed. All right. I don't want to keep people here that late, so we can revisit this. All right. So just so that all of us remember, and this was some work on. So actually, Hojin might try his hand at understanding how much representational information or how much representational non-redundancy is in the two hemispheres. So Hojin, with your permission, I'll just outline the experiment that you're planning to do. So Hojin has access to a public fMRI data set, not this one, but something even bigger. So 8 participants looking at thousands of natural images, drawn from how many categories, Hojin?
Like 80.
80 categories. So, and each one looked at 10,000 images drawn from 80 categories. So you have event-related information for each one of those images. So what Hojin is going to try to do is to decode the category information using just one hemisphere. So let's say n voxels from one hemisphere, or n by 2 voxels from each of the two hemispheres, and see whether by having the two hemispheres, one improves the decoding accuracy, which would suggest that there is non-redundant information across the two sides.
But how can you rule out just have more sample and you find averaging over more voxel, you actually you have more increasing signal to noise ratio.
Well, so he will have to keep the same overall number of voxels in the two.
But
settings.
however, the same number, but however, it's like overlap the two. It could be different within the hemisphere versus.
Yes,
of course. Okay.
within versus.
Okay, that makes sense.
Yeah,
Okay, that's
yeah.
okay.
Right. So we are on pins and needles to find out what the answer to that.
Okay, that would be very interesting analysis. Yeah.
We just talk.
And you will present his results next week.
Analysis?
Yes. But you have already downloaded most of the data.
Yeah.
Yes. Yeah. All right. So the next time when we meet, this Charlie, we have already looked at the reason into visual body.
Yeah, we did this one, I think.
We did.
I'm pretty sure.
Yeah.
Everybody thinks so. Okay. And did we do this?
I don't think we did this one. I remember.
Okay, so this is
Oh, this is interesting.
new. And so we'll do this, not today, but on a later day. And this one,
I don't think so. No.
No, we didn't do this.
okay, so these are
This
the,
one, that.
and how about this?
I don't.
Oh,
think
this will be
I don't
controversial.
think we did that. I don't think we did.
No, okay,
So
so
this is a good one.
so 3, this we did, I know,
Or
dynamic sequences.
Yeah. We
Yeah.
did this.
Oh,
Yeah.
That's why we skipped to that one, but. we have
Okay,
those
okay,
three.
so we have
Yes, we
3.
Cherry pick. Quite interesting.
Hmm?
See many things, right? Mhm.
So we will do this, this, and this.
What does that one say? The previous one?
What, this?
Too bad. This one.
Hmm.
What's it called? Basic perception.
And maybe trying to discuss this
Perceptual
question.
consistency.
Size constancy. Is that like something appears the same if it's far away? Which is, that's that's very interesting actually.
Mhm.
It's like if this wine bottle is like right here
Right.
versus if it's like at the end of the table, it looks very similar in size, whereas over here it's falling on like 10 times as much retinal space as over there. So like it's 10 times larger on your retina,
Mhm.
which
Yeah.
is actually
Yeah.
and how we recognize objects across
Great,
across
Right.
that issues.
Mhm.
okay.
But next week we will hear some.
Next week we'll hear from Jiten. Jiten, are you still there?
Anshul made
might
a
have
comment
asked.
also.
Anshul made a comment?
Yeah,
A
let's see
question,
what it
yeah.
is. People use one thing.
Will one of the limbs or eyes early have any
Mhm.
altered
Activity
in one of the lobes?
Ella would have been a good person to
Yeah,
answer
yeah.
this.
Ella, so the next time we could.
I think those,
Yeah.
so those parts get like other areas sort of
Mhm.
use that space, but
Right.
whether just the other lobes.
So there is just to that specific question, Mike Merzenich did these studies with monkeys
Mhm.
where so each of our digits has a representation in the somatosensory cortex. What Mike did is to amputate one of the fingers of the monkey. Now that section of the cortex in the somatosensory region has been deafferented. It's not receiving any input from
Mhm.
the correct finger. So the finger that has the adjacent cortical area that expands, and that finger takes up the vacated spot. So this finger now has much more cortical representation than what it originally had. Interestingly, however, that expansion of the cortical representation has no effect on the sensitivity that this finger has. So even though it's getting more resources neurally, there's no behavioral
Yeah.
benefit.
Very similar to amblyopia.
To
In
amblyopia, right,
there
exactly.
was like the ocular dominance
Mhm.
column.
Mhm.
Actually, like one is deprived,
That's right.
of the poor eye, and then expanding for the other eye. But however, in terms of visual acuity, doesn't really exceed super visual acuity consciousness. So this is normal, right? So
right.
it doesn't make sense if you're holding more neuron.
Yeah.
You're expecting more computation, but
Right.
it's a have like it's kind of the cap on
Mhm. Right.
Do you know about like squirrel monkeys and their ocular dominance columns? Like some have like really thick, some have very skinny, and some have like none at all.
Mhm.
Yeah, that's like very
Is it
interesting.
following molecular deprivation or
No,
just
just from birth.
normal? From
So it'd
birth.
be like an interesting animal model
Do they
to try to
actually
understand if there's any function. Huh?
measuring their visual function? Whether
I don't know if
it's-
there's a lot of experiments on
what's the functional consequences of that?
Mm.
It just
So-
yeah, I
varies.
mean they all survive, right? Like it's something that's been carried on. It's not like there doesn't seem to be any like
So-
clear deficits.
So Jitendra, who will be our next speaker, he might have something to say to that, because I believe Jitin had maybe worked with squirrel monkeys. But yeah.
So I think so.
So my question,
Hmm.
like, is it that they didn't have low sensitivity just after the amputation, but
Mhm.
would they have been trained to sense a little more, right? Like
There's
would
more
the capacity of
potential.
to learn would have
Oh,
increased,
okay.
right?
So
After
if you
training,
train, you
Yeah.
actually, maybe you could reach better.
more, I don't know, more sensitivity or better.
capacity.
Yeah, because that's how human, like,
Mm.
Oh,
Jitin gave that
okay.
example of
Uh-huh.
my dad had a
Mm.
stroke on
Yeah.
the right side, and after a lot of physiotherapy, his other part of the brain picked up that.
Mm.
Right? So,
Or also, I think because of the you have a like sensory, like very low level sensory, like the neuron limitation. But however, always cortical. No matter how much cortical information is devoted, you're maybe you're limited by the very low level your like sensory limitation, right?
Mhm.
the
So
neural
that-
pathways need to
yeah,
be
yeah,
trained.
exactly.
Yeah,
Yeah,
yeah.
exactly. Like, the eye probably the same, even though you have more cortical resources devoted to the
Mhm.
fellow eye, but because of the retinal neurons, it doesn't
They
really
simply
change.
cannot signal any
Yeah,
finer
signal,
frequencies.
right.
Yeah.
So I think they're limited
Yeah.
by different,
Yeah,
like,
yeah.
different stages of visual processing.
Mhm, mhm.
Mhm.
Yeah.
But however, I think like the going back to your question, whether there's like training
Great
or
capacity
just
to learn,
learning can
yeah.
actually break that ceiling, that's another question. That's really interesting.
That would be great.
Mhm.
Yeah, yeah.
Mhm.
All right.
Okay,
Thank you.
That's a really good.
Yeah, yeah. The meetings are always so invigorating. Michal, Shoaib, Jason.
Not this.
Thank you
Thank
for
you,
organizing
Michal.
this. All right.
Toast.
Thank you to everyone for joining online. And we will reconvene next week and hear from Jitendra, who will tell us about neural development.
Mhm.
Cool. Okay.
Yeah.